I'm now going to talk a bit about parsing and code generation. So parsing, this concerns the entity example. As you recall, in the entity example, we can define entities that might extend other entities and that have fields, and fields have a type and might have a name and might have an inverse. Um, and we can use the concept of a BNF to define what kind of syntax we allow for our entity system. So, and here is sort of this is a fairly complete BNF. So as you recall, BNF is in fact a domain-specific language, somehow an informal one, but nevertheless a domain-specific language for defining languages, the syntax of languages. So here we say a system. An entity system is a sequence of types. Types might either be base types or entities. A base type uses the keyword type and then an ID, which defines the name of the base type. An entity, on the other hand, uses the keyword entity, some text, and ID, which defines the entity. There might be extends another ID. We put the question mark to indicate that it might be there once or might not be there at all. Then a left brace, a bunch of fields inside, and then a right brace. A field has an identity, ID, which is the name, colon, and then there might be a star, which defines that it's a multiple relation, an ID, which defines a type, and then there might be the keyword inverse, a colon, and then the ID of the inverse, and it might be there. IDs are defined by a regular expression. We haven't talked so much about them, but this means that first we have a letter, A through Z, or lowercase or uppercase. Note that an underscore is not included, so underscores are not legal parts of identities here. And then we have the rest of it might then be letters or numbers. So this defines the language that we want to use. If you, when reading a BNF trying to apply it, you can sort of see it as rules where you descend into each of them. So when you encounter something you want to pass, then you have to go down inside the rules, like if you're doing recursive calls. So this lends itself very well to implementation as a bunch of recursive methods that then call down into the subclasses, but it becomes difficult if the grammar is a bit complicated, like when we add base type or entity, which method should we call? Should we call the parse a type or the parse an entity method? And that's where the parser generator comes in and does a lot of useful magic for us. But how do we parse? So we talked in class, people had different suggestions. One was to think of it like a state machine. So we start in the state where we want to say, oh, we want to pass an entity. Then we first pass the keyword entity, then the ID, and then we might either pass extends, whatever, or pass a left brace, and we get here eventually. Then we get inside a pass a bunch of fields, and then we go back here. So the problem with plain state machines is that they cannot do nesting like this, nested things. It just doesn't work. When we have extended state machines like we use sometimes in class, in fact, it's more general, but basically state machines are not very good for this. We normally use what are called push-down automata that can keep track of nesting. Then we're fine. Another intuition was to collect what is called an AST, an abstract syntax tree, a data structure tree shape that represents all of the information we're finding. So a system, a concrete system we are reading from a grammar might have an entity, person, and some other entity, a bunch of fields inside the person. Each of these fields subtrees is then has a name, which is a string, and whatever. So the AST is represented precisely the information in terms of tokens and structure that we are extracting from a concrete parse. Note, however, that there's no relation between different entities. So an entity person that extends or teacher that extends an entity, a person entity, well then different parts of the tree, and there's no relation between them as such. Whereas what we really wanted to have was something where there's a system that has a bunch of types, and entities might have relations to themselves, and fields have relations to types as well, for example. So if we want to build a system like that, then we don't want the ST, but of course then we can use a symbol table. A symbol table can, using it, we can then search through whenever we have a teacher that extends something, a person, then we can search through the system and find the thing that it extends and then connect them. Ultimately building this object structure here. This is precisely what xtext does for us. So we look at the BNF. In xtext, we can basically write the BNF, and for each identifier, we need to say what kind of thing is this defining? A name or whatever. Name of an inverse, name of a type, name of the field. And then xtext will directly build this semantic model for us rather than having to go through the AST and without having to worry about exactly which sequence should we do things to be able to parse it. So parsing. Now code generation. Here there's a small slide about code generation. So if we have a small system like this with a student with a name and an age, how would you generate code from it? If you were to write plain Java code, then would be something like this. For each of our entities, generate the code for this and then write it to a file. And generating code for a class, when maybe we need a string buffer, and then we append to it public class, whatever. We might need to extend something, but that's not included here. And then for each of the attributes, append private and plus and quotes and spaces and lots of things that are hard to read. And then ultimately we will get this over here. This works, but it's not a very convenient language. In another video, which will appear shortly, we're going to talk just a bit about other languages that have more convenient syntax for generating code. And one such language is, of course, Extend, that is part of the xtext framework, where we have both our template expressions, where we can write code more cleanly, and we have other things that help us to generate code in a nice and concise way, such that we get more easy to read and readable code generators. Regarding Extend and code generators, here's something about the generation gap pattern. So here on the left, we imagine having our state machine language, and we want to write something like power equals the square root of power, or calculate something or whatever. And we would like to not define square root and whatever as part of the grammar, but we want to be able to say that, oh, these are external functions that we define somewhere else. They're not part of our DSL. DSLs typically only want to include the very specific things, not all the general things. So we want to say square root, sine, cube, or whatever, external functions. But how do we attach these to the generated code in a robust way that if we change the name of one of these functions, like adding an e to sine, then we somehow learn that now there's a problem. And the way we do this is to define or generate whenever we collect all of the external functions that are declared. So here we declare them, and then we collect all of the ones that are declared, and we generate based on these an interface. So we generate an interface that lists exactly those functions. And now in the end, if we, just going to, this might not work so well. In the end, maybe our state machine code is generated something like public. This is the cooking hood state machine. So public class cooking hood state machine. And this is generated code. There's a whole bunch of things. And then the constructor, public cooking hood state machine, should take an externs as an argument. Externs, like this. So whenever we create a state machine instance to actually do something with it, we have to provide an implementation of the external code, which we then write in Java. If we were to generate C code, we could of course do it in a different way. And so how does this work in terms of how we work with a and how does so this is sort of a general example. So here in the middle we have an example of using this generation gap pattern. How do we generate code using extend for expressions? So expression might be so in extend we would have something like, so I'm just going to use the same text box up here. We have expression which is either a number, oops, might be a number, or parenthesis, or an addition, or a function. And numbers are just numbers. Parentheses contain something else inside them. Addition has a left-hand side and a right-hand side, and a plus in between. And functions are calls to external functions. Now, in extend, we use the feature of multidispatching. So we can define the compile method such that it takes different types of arguments. And the compile method is then going to, at runtime, look at what kind of object do I have. If I have a number object, where we have an expression, if it's a number object, then do this, which is just insert the value of the number and dot val here. If it's a parenthesis, then just take what's, there's actually a small error here. It should be not p.compile, but p. whatever is inside me .compile, otherwise it's an infinite loop. But put parentheses around it and then generate code recursively for whatever was supposed to be inside the parentheses. If it's an addition, then compile the left-hand side, put a plus in the middle, and compile the right-hand side. Or if we needed to do something like big nums, then we call the add method. For functions, well, then we say this.xturns, which we know we have because the object that we're running inside when the generated code runs was provided this as a constructor argument. Call the name of the function and then put each of the arguments in there. So a function call has a bunch of arguments, and then we have the neat feature here for the template, generate a bunch of code with a separator colon, comma, to compile for each of the arguments info. So this will generate a nice long list of calls. We probably need a semicolon. No, we don't. Sorry, no, we don't need a semicolon because we're in the middle of an expression. So generation gap and a bit of multidispatching to make it convenient to write in extend. Thanks for watching.